In this video, we're going to talk about the following limit using the limit definition of the derivative. So we're going to talk about the limit as z approaches infinity of 3 minus 5 over z. And we're going to show that this limit is equal to 3. And so we're going to do this using the not quite epsilon and delta definition, but the epsilon in n definition of a limit. So what we want to do is we want to show that for all epsilon, there exists in n so that if the absolute value or the modulus of z is larger than n, in other words, if z is sufficiently far from the origin, then our function gets arbitrarily close to 3. By arbitrarily close, I mean pick as small a value as epsilon as you want. It'll be within epsilon of 3. So this is what we want to show. And so what we can do just to start with is to do just a little bit of rearranging here. So first, before we actually go through this, I want you to notice that I should point out that in the book, the way that some of these problems are written, and this is true of any calculus book, any complex analysis book, any real analysis book, almost universally, where I say notice, I'm going to do some algebra stuff. This often gets just hidden away, and then the proof gets given to you, and it looks very strange. Why are we making this choice of n and epsilon and delta? But let's just go through it. It seems much less mysterious if we do the algebra ahead of time. So I'm going to notice that if I take our function f minus our limit L, so that's the 3 minus 5 over z, that's our f minus L, that's equal to 5 times the modulus of 1 over z. Because the 3's cancel, the negative 5 you can bring outside. You can treat that as like a absolute value if you want. And then we're just left with the modulus of 1 over z. Or if you like, you can even write it to make this even more recognizable, 5 over the modulus of z, right? So whichever you prefer. But this is important because this is going to be less than epsilon when the modulus of z is greater than 5 over epsilon. So pick an epsilon that's as small as you want, as long as you pick a complex number whose modulus is at least this big, right? If epsilon is, say, 1,000th, then this 5 over epsilon would be 5,000. So pick the smaller the epsilon is, the bigger this quantity gets, because we're talking about positive numbers here. And so if you want to get arbitrarily close to 3, if you want this function to be arbitrarily close to 3, meaning that it's within epsilon, that can happen as long as z is big enough. So here, all we have to do is we just have to check. And this is kind of the work that's done ahead of time. Now we just need to look at the argument and make sure that it works. So let's let n, capital N, be 5 over epsilon. And if that's the case, then assume that the modulus of z is greater than n, and then f of z minus L in absolute value is going to be, like we've already done this part, it's going to be 5 over the absolute value of z, which is going to be, so notice that if the modulus of z is greater than 5 over epsilon, so here I think it's useful to write this as 1 over z. Since the modulus of z is bigger than 5 over epsilon, then 1 over the modulus of z is going to be less than epsilon over 5, right? Because when you reverse the inequality, you flip it, and vice versa. And so this is going to be less than 5 times 5 over epsilon, which is epsilon, which is exactly what we wanted. Okay, so the point here is that if we pick capital N to be 5 over epsilon, then we win. Then we get everything works out very nicely according to this limit definition. Okay, so this is the formal definition of a limit.